Hello everyone, welcome to week 1 of the second course in statistics that you're doing in this program. We'll begin by looking at the basic concepts of probability and how to model random phenomena using probability and all that. So everything starts with a few very basic important ideas, and these are the ideas. There is something called an experiment, there's something called an outcome for the experiment, there's something called sample space, there's something called event, and finally we'll get to probability. Okay, so it's important to go in the sequence. We'll do that slowly in this lecture. So before I start, let me talk briefly about textbooks for the course. There's one textbook that we'll follow reasonably closely, which is the first one that I've put down here, Probability and Statistics by Shiva Atreya, Deepayan Sarkar and Steve Tanner. It's available from Professor Atreya's website. You can click on that link there and go to the website. As of now, it's available. It's work in progress, so they've not completed the book, but we're using it even before they complete it. So we'll follow this book fairly closely in terms of what topics we cover, what examples we use, the sequence in which we do it, etc. A couple of other books which are useful. One is what I'm going to call what I've put down here in the second list. Think Stats 2. It's a very applied book. It talks about doing statistics with Python and then lots of ways to do computer simulation. And in this course also, we will do quite a bit of computer simulation. So mostly it will be me showing you how the simulation is done. You don't have to do any programming or anything on your own. But what computer simulations allow you to do is to sort of see in action what we are writing down as equations in theory. So quite often it's useful to imagine what's going to happen when you do a computer simulation. So we will do that quite often in this class. So a book like Think Stats 2 is quite useful. It's also available for free download, so you can use it without any cost. Now the third book is a little bit more theoretical, A Modern Introduction to Probability and Statistics, and it's a little bit more expensive. So if you want more ideas in this area, this you can use for like a reference. When you want to look at other ideas, related ideas, more details, you can look at that book. Okay. So in fact, there are so many books. You go to even websites which talk about good books on probability and statistics. You have so many books, so many different types of options. I mean, any book is good enough. You can at some level, right? So, but you may like some books, you may not like some other books. The approach and the way they handle it may all be very different. But you're free to just browse through any book that you like. I'm not against it. So none of these books are strictly necessary, as in I will cover most of the things myself, but having a book is very, very useful. You can go back, sit down, browse through the pages. You'll get some ideas when you read again. Okay, so I'll strongly advise that you have access to some of these books. Keep reading them while you attend these lectures. Okay, so that's the first slide on the textbook. Okay, so we're ready to jump into the very first concept in this course. There are two concepts that we're going to start. Concepts or definitions, or I think definition is probably a better word. Experiment and outcome of the experiment. Okay, so when I use the word experiment, you're thinking of a chemistry lab, scientist with a lab coat and all that. It's not quite that. Need not be exactly that. In statistics, experiment is generally used to denote any process or phenomenon that we wish to study statistically. Okay, so that's called an experiment. So the experiment would have various different outcomes, and we would like to study it in a statistical way. I described in the first lecture on what it means to study something statistically. It's basically to observe patterns and have some theory about what those patterns are. So I've put three different examples here, familiar examples. We discussed that even in the week 0 lectures. Tossing a coin is a good example of an experiment that one can study statistically. Okay, and throwing a die. Okay, the result is varied. There are different types of results and all that. When you can't really precisely say what the result will be, so that's a good experiment. And we also saw this very complicated experiment, so to speak, which is like the Indian Premier League tournament. We looked at that as an experiment as well. We wanted to study that statistically. So all these are experiments. So in fact, it looks like anything is an experiment. So the point is, when you want to study statistically, see if there are patterns, statistical patterns in the data or statistical pattern in the phenomena, you use the word experiment to denote that. Okay, so you'll see quickly enough in about 3-4 slides down from here, I will never use the word experiment, but technically that's the word that's used. Experiment is what you basically model. Okay, now outcome is very important. What is the outcome? This is the result of the experiment. What happened as what did you observe in the experiment? You can even call it data, right, in some sense. So the outcome is what's very important. So you'll see the theory focuses a lot more on the outcomes, and the experiment itself is sometimes even you can imagine what the experiment should be. Okay, so I've listed down below the outcomes corresponding to each of these experiments. For the coin toss experiment, there are 2 outcomes, right? Assuming it's a standard coin, it's either heads or tails. For throwing a die, 1 die, okay, right? It's either 1 or 2 or 3 or 4 or 5 or 6. That's the possible outcomes. And if you go to a complex experiment like the Indian Premier League, you're not going to be able to write down the outcomes so easily. It's for instance, it could be available as a YAML format file. We discussed this format in the week 0 lecture, right? So to capture the result or the outcome of an experiment as complex as an IPL match, you need a lot of text and typing, and you need to capture what happens in every ball. Even then you may not capture everything, right? So you might think the only thing you want to study statistically is the number of runs scored and wickets, etc. on the ball. But people who want to do research in cricket want to know, where did the ball pitch, what is the pace of the ball, did it turn, did it swing, did it do this, that, etc. And all those are also patterns, right? You may learn some patterns from that. So I mean, technically, I would say experiment like the Indian Premier League match is like very rich in the kind of outcomes that it can generate. Okay, so that's so this probably gives you a glimpse of what is it that you can study. So, for instance, you're studying rainfall. You want to see statistically how the rainfall pattern is. What is the experiment? Right, who is doing the experiment? So it's like nature is doing the experiment, right? So there's this big system of clouds and wind and sunlight and oceans and all these things together create these rainfall situations that happen for you in India, and then you study it, and the outcome you all measure, right? So how much did it rain? What was the pressure here? What was the pressure there? This, that. The people send balloons up in the air. So you can measure whatever outcome you want. And collect as much detail as you want whenever you want to study statistically, and the experiment is something like the phenomenon that you want to observe. Okay, so hopefully you get this sense. So I want to tell you that we will look at a lot of toy experiments. You can see the toy experiments, simple experiments to study are tossing the coin, throwing a die. Now, why are these simple experiments important? If you cannot do something in the simple experimental world, you really cannot do something in the complicated real life world. A lot of people look down upon theory and say, oh, you deal with small toy examples, but if you can't do the toy examples properly, very likely that you will make mistakes in the bigger examples as well. So you have any ideas, you want to try something, you want to try them in the small toy examples first, make sure it works, and then adapt it to complicated scenarios. So don't look down upon the simple experiments. They are nice. It's good to illustrate, it's good to teach out of, it's good to ask questions in exams sort of. So all these small experiments are very nice that way. Of course, in real life you want to study complicated experiments with a very rich set of outcomes, and you'll see, I mean, quite often we'll use some ideas from simple experiments in the complicated studies as well. Okay, so hopefully this gives you a feel for what experiments are. There's so many of them. Anything you study statistically becomes an experiment in some sense, right? So that's something nice to know. Okay, so we've seen experiments, and like I said, outcomes are very important. The outcomes of the experiment is really what you study statistically, really what you look for patterns in, right? So that's why it's very important. Okay, but I mean, experiment is also equally important. The physical aspects of it, what you know about what happens in the experiment, right? When you know cricket really well, maybe you know what patterns to observe for. okay, right. So your understanding of the experiment is also very important, but nevertheless for the theory and definitions and equations, the outcomes are central. Okay, all right. Okay, the next important definition is that of a sample space. Okay, so I've put down the definition here in this little box, which says a sample space is a set that contains all outcomes of an experiment. Okay, so first thing you see when you in a definition is when somebody is trying to define something, you have to see what it is, right? Usually, when you define something mathematically in a precise way, you have to say something is a certain mathematical object, right? So that's only then it becomes precise in some sense. You can't be vague about the definition. So in this case, you saw that experiment and outcome were not very precisely defined in some sense, but the sample space is a very precisely defined mathematical object. It is a set. Okay. What does it contain? What are the elements of the set? The elements of the set are all the outcomes that can possibly happen in an experiment. Okay. So, like I said, sample space is a set, and we will denote it typically in this class by some S. So this capital S will denote the sample space for us. Let's look at examples. Right. Anytime you have a definition, the first thing you should do is write down a few examples. Okay. So look at the examples we saw before. We saw 3 experiments that I listed out. I'll show you a few more experiments in this lecture itself. Some may be more complicated, some may be very simple, but we will start seeing them in this lecture itself. So let's look at tossing the coin, right? So what's going to be the sample space in this experiment? It's going to be a set with just 2 elements, heads, tails, right? So it's easy enough. Throw a die. Again, the sample space is very easy. There are 6 outcomes. You collect them all together into a set. It becomes your sample space. Now, if you now jump from the small toy experiments to the big experiment of the IPL, you see that sample space is really difficult to write down, right? So it's basically the set of all possible things that can happen in an IPL match. I mean, depending on what level of detail you want to look at, the sample space can be very, very complex. Like for instance, if you only were to be concerned about runs scored in one delivery, right? You can have a sample space which is very simple. It could be 0 or 1 or 2 or 3 or 4 or 5, 6, 7. Can 7 runs be scored? Yeah, I mean, it can happen occasionally. So all of this you may want to write down. That's easy to do. Or maybe you're interested in just the winner in IPL 2021. Maybe that's what you're interested in. In that case, if that's the only detail you care about, then your outcome is very simple. I read recently that there are 9 teams that are going to be playing in IPL 2021, and you might want to list out all the teams as into your sample space. So depending on the level of detail you want, even in a big experiment, the sample space can end up being small, right? But nevertheless, the experiment itself is so rich, the set of outcomes are so rich, like an IPL, that you can do a lot more. But maybe this gives you a sort of a hint as to what to look for when you think of sample space and all that in real life. Okay, so having said that, having defined a sample space, I'll also have to tell you that quite often in practice, once you get some comfort with all these notions of probability, you will hardly ever write down the sample space for a problem. Okay, so you will sort of imagine that there is a sample space. There is always a sample space, let's say, and once you understand that there is a sample space, you will be able to work with probabilities directly. You don't have to really explicitly write it down. But quite often, what I've seen, at least in practice, is when you get really confused about what some definition has to be, you're not clear about some definition, you don't know how to think of something, you're confused. In those kind of situations, writing down the sample space can give you a lot of clarity. Okay, so in that way, sample space is quite useful. It's a very important theoretical construct. The entire probability theory builds on it, but nevertheless, in practice, usually, once you see the problem, you just write down the probabilities and start working with it, as opposed to thinking of sample spaces. But still, it's important to know. Somebody describes an experiment, talks about the outcomes of the experiment, you should be able to identify the sample space of interest to you. Okay, so that's very, very important. Okay, so here are more examples. So I gave you 2 or 3 simple examples. We're going to now start talking about more and more complicated examples. And these examples are nice because they will show up again and again in all your problems, in all your activity questions, graded assignment questions, practice questions, quiz questions, exam questions, other questions, whatever. And even in real life, these kind of experiments and outcomes and events and sample spaces will happen again and again and again. So it's good to sort of get used to what we mean by this. Statisticians love what's called the urn, URN. You won't say pot or jar or some box or something. They'll say urn. For some reason, they like the urn. Urn is just a pot. Okay. The first experiment that you see there is drawing a marble from an urn. Okay, so marble balls, people use different things that they put inside the urn and they start drawing one after the other in different ways, and it's a very nice illustrative experiment in which you can write down things, do calculations. It's quite useful. We'll see this experiment is very interesting. We'll keep revisiting this in various different contexts. Okay, so you have an urn, there is this pot. Start opening up your imagination, right? So think of a pot and it has marbles of many colors, right? So for example, it could have 3 marbles of red color, 3 marbles of white color, 3 marbles of blue color. Okay, so it's all inside the pot, and so you're going to draw a marble from it. What do I mean by that? You don't see what's inside. You just like close your eyes, put your hand inside, and pick up a marble, right? Now, what is the outcome of this little experiment? Drawing a marble from an urn which contains marbles of many colors. It's the color of the marble, right? So that's what we are interested in. So if you want to write down a sample space for this little experiment that we have, red, white, blue would be a very good answer for that sample space. So that's a good sample space. Okay, so now what happens when you draw 2 marbles? Right, so you see immediately when you complicate the experiment a little bit, the sample space starts to get bigger and more interesting and has a richer structure from which you can do more calculations. So immediately you have to ask, when you draw 2 marbles, how do you draw them? Do you draw them simultaneously, or do you draw them one after the other? If you do one after the other, do you put the first marble back and then pick up the second one, or you keep the first marble away? So these two turns out are different examples. They give you different experiments. Even though the outcome and the sample space and all might be same, the experiment suddenly changes when you do with replacement and without replacement. So what do we mean by that? Once again, you have an urn with a lot of marbles. You're going to pick 2 marbles one after the other. Okay, so you pick the first one, and then you pick the second one. Now it depends, the nature of the experiment changes depending on whether or not you put the first marble back and then pick the second one, or you kept the first marble away and picked the second one, right? So that's 2 different things. So people will talk about drawing 2 marbles from an urn with replacement, drawing 2 marbles from an urn without replacement. Okay, so you'll see people distinguishing these 2 experiments, and the calculations you do change based on that. But hopefully I want to convince you that the sample space starts to get more and more complicated. I mean, if you want to keep writing sample space, what are the possible outcomes? Let's say, let's say you start with 3 marbles of red, white, blue, an urn with 3 marbles each of red, white, and blue color, and let's say you're drawing 5 marbles, right? I mean, as you keep increasing the number, so you see now you have to think about what would you put in the outcome, what is possible, etc. You cannot have red, right? You cannot have that, right? So there are only 3 red balls. So you have to think of all that, and it starts to get confusing in your head. So that's one of the reasons why people don't tend to write down the sample space in all its glory. They just think and they understand, okay, there has to be some set of outcomes. I understand the outcomes. I draw the balls marbles one after the other. I note down the color of each marble, either there was replacement, there was no replacement. So I know what could have happened, right? Just once again illustrate this replacement and row replacement. If you have 3 marbles of each of these colors, and if you do with replacement, one of your outcomes is red, right? You can have 5 red marbles. But if you're doing it without replacement, you cannot have red, isn't it? Because there are only 3 red balls. If you're not replacing, you can have at most 3 red balls in every outcome. So So anyway, I mean, I want to drive home the point that there are these nice simple experiments which which can quickly give you more complicated sample spaces that you can think of. Another very common example is a pack of cards. Okay, so now many of you maybe are very sincere students who have never played or seen a pack of cards, but I'm assuming you're at least familiar with what a pack of cards is, at least for the reason that you have to solve questions in the problems here. So a pack of cards is 52 cards. There are 4 suits. The suits are in English called spades, hearts, diamonds and clubs. So there are different names. I think in common parlance people use different names for these 4 suits, but we will use the spades, hearts, diamonds and clubs. And in every suit you have 13 different cards of different values, right? The cards start with 2, 3, 4 all the way up to 10. And then you have the jack, queen, king and ace. Okay, the ace I will put at the end. Some people tend to put the ace in the beginning, but we'll tend to have it at the end. Okay, so the sample space, one can conveniently write it as the Cartesian product of these 2 sets. Okay, the set of suits, Cartesian product with the set of values. Okay, recall Cartesian product from math 1, right? So you remember Cartesian product, you have 2 sets. When you do Cartesian product, it's basically a pair, one from the first set, another from the second set. So in the 52 cards, there is 2 of spades, 3 of spades, 4 of spades, so on till ace of spades. There's 2 of hearts, 3 of hearts, 4 of hearts, all the way till ace of hearts, etc. So you have these 52 cards. Okay. So when you draw a card from this pack, let's say a shuffled pack, then the sample space is this set of 52 cards, right? So what would be the suit, what would be the value. Now when you draw multiple cards one after the other, or like it happens in a usual card game, you deal or distribute the cards to the players. What could happen from a shuffled pack if you start distributing cards? Let's say 4 players are playing and you distribute the cards, each player would get 13 cards. Now look at the possibilities there, right? The sample space of what one player would get is a subset of 13 cards from this sample space. And how many such subsets are there? A huge number, right? 52 choose 13. That's a lot of possibilities. Okay, and anyway, I'll come back to this experiment. It's a slightly more complicated experiment, but it'll bring out a lot of statistical patterns that people observe. For instance, you might see that different collection of cards are likely, some card selection from a random distribution are unlikely and all that. So you may have a sense of what can happen, what cannot happen when you distribute a pack of cards, but it's a useful experiment, very useful experiment to think of when you want to solve problems. And hopefully you agree with me that the sample space is slowly becoming more and more complicated when you want to think of modeling, say, distributing cards around a table statistically. Okay, so the last point I want to mention, okay, so we discussed quite a few experiments now. We saw tossing a coin, throwing a die, this complicated IPL experiment, and drawing a marble from an urn or a ball from an urn, drawing a card from a shuffled pack. We saw quite a few experiments and we talked about the sample space, etc. But I have to warn you, so as you learn more probability, once the problem is given to you and you have to compute the chance of something, the likelihood of something, what is the probability of something, you will usually not write down the sample space. I mean, it will be in your mind sort of clear to you how to do it. So I want to emphasize once again, it's still very useful when some question confuses you about what can possibly happen. You can always go back to writing down the sample space, writing down the outcome in very clear notation, and then invariably, at least I've seen in practice, that helps get rid of all the confusions and the paradoxes and all these things that show up in probability calculations quite often. Okay, so hopefully you've gotten your feet wet with sample space. Let's dig in deeper into the theory.